Hi everyone, I hope you guys can hear me and I hope prelim preparation is going well. Can I just get an indication in the chat? How are we feeling about the upcoming prelims? Are we excited? Are we confident? Out of 10, let's just gauge where we're sitting at with physics. Some are saying 7, some are saying anxious. Let's hope that by the end of this, we will be at 100% or at least better than we were when we started. I'm going to start by introducing myself. My name is Muranga. I am a student at the University of Pretoria and I study industrial engineering. Today, we will be going through momentum and impulse. So let's get into it. I'm going to share my screen shortly. And in the meantime, while I'm setting up, please share the link with your friends and any others that may or may not need the help. Just give me a second, guys. I'm about to share my screen. In the meantime, you guys can just engage in the chat to make sure that you guys can still hear me. And yeah, just update me guys on how you're feeling about physics, how you feeling about chemistry, and how did you find yesterday's session? I hope that you guys found it very informative and it helped your understanding of, I think it was number patterns that was covered yesterday. All right, guys. We are doing momentum and impulse. Again, my name is Muranga Dao. I'm a student at the University of Pretoria, and I'm hoping that we're all ready. For those that weren't here to join us yesterday, our sessions are recorded and posted onto our YouTube channel. And you can find this content along with everything else on our socials. That includes Instagram, TikTok, and YouTube. Please follow at the linkspace.a and send to all your friends that may need assistance. Cool. Let's get into it. What are momentum and impulse? You can think of momentum as mass in motion. This is essentially the oomph something has. So if something has a higher mass, it has a high momentum. If it has a higher speed, velocity, then it has a high momentum. For example, you could use a truck and a bicycle. A truck traveling at 10 kilometers per hour will have a higher momentum than a bicycle traveling at the same speed. And that's because of the formula, momentum is equal to mass times velocity. It is mass in motion. Impulse, on the other hand, is a change in momentum, usually caused by a force acting over time. The best example that I can give would be, consider cricket players. When they want to catch a ball, they move their hand with the motion of the ball to reduce the force and the likelihood of it bouncing back. In the same way that in tennis, for those who have played, if you want more power behind your, I think it's called a swing, if you want more power when you hit the ball, you have to follow through. And that following through allows the ball to make more contact with the racket and thus increase kind of the force acting over time, if that helps you guys understand these topics. I have included some formulas that you would likely be using today, and this is just for your guys' benefit. So please make every effort to try recall these, or at least have your writing instruments, your calculator, as well as your formula sheet ready. Cool, we're gonna jump straight into it. We're gonna start with this multiple choice question. Which one of the following combinations is true for an elastic collision? First of all, guys, in the chat, can you guys answer me? What is an elastic collision? Okay, somebody's saying I should speak louder. Okay. Someone in the chat says that an elastic collision says that we have the same kinetic energy. Someone else says that the kinetic energy and momentum are conserved. And yeah, it seems as though, yeah, you guys generally get the idea of what an elastic collision is. This is a collision in which momentum and energy are conserved. There's no loss of energy. It's important for us to remember our conservative and non-conservative forces, guys. An example I could give for a non-conservative force would be friction. There's energy lost due to friction. So let's get to actually tackling this question. Our options are A, conserved, conserved, B, not conserved, not conserved, C, conserved, not conserved, and D, not conserved, conserved. I'm seeing mixed answers in chat, but the actual answer for this question is A. When we have an elastic collision, both the linear momentum and the total kinetic energy are conserved. So yeah, it is important for us to just recall our definitions for all these things. Fine. Now that we're done with that question, let's move on to the next one, unless there are any questions in the chat. If you do have questions, please post them in the Q&A section. Dinyiko's asking, why is it A? Dinyiko, in order for this answer to be correct, or in order for A to be correct, we just have to remember how we define elastic collisions. An elastic collision is a collision in which linear momentum is conserved as well as the total kinetic energy, right? And that just means that there are only conservative forces at play. Cool. For this one, this answer really relied on our knowledge of conservative and non-conservative forces, guys. All right, let's move on to the next question. Right. So for this question, we're given a graph. The graph below represents the net force acting on an object over a period of time. In the y-axis, we have F net, and in the x-axis, we have time. We want to find the area under the graph, and we have to relate it to one of the options we were given. Which answer do you guys think it is? Remember, we want to find the area under the graph right here. The answer to this question is, in actual fact, impulse. And that's because impulse is defined as the product of the net force acting over time. F net times delta T would give us impulse. Usually the symbol associated with this one would be J. Miketsi asked a question, why is the answer for the previous question A? Miketsi, we have to understand what let me check. Yeah, we have to understand what an elastic collision is. There is no loss in energy. Remember, when we have no loss in energy, that means there's only conservative forces at play. So for that one, please revise your definitions. Right. Now that we're done with this multiple choice question, I'd just like to check with everybody in the chat. How are we doing thus far? Is this jogging your guys' memory? Cool. Seems as though we're all positive on this one. So let's move on. Now we're going to start with the actual calculations. Two ballet dancers, A, of mass 52.5 kilograms, moving with a velocity of v meters per second in a straight line east, and B, of mass 42 kilograms, moving with a velocity of 4 meters per second to the west in a straight line, approach each other as shown in figure 1. The two dancers grabbed each other and came to rest as shown in figure 2. Ignore the effects of friction. This means that we are dealing with a system that is isolated. There is no loss of energy in this case. So where there is no loss of energy, we have to remember the principle of linear momentum. Cool. So let's get to answering this question over here. We want to calculate the velocity of dancer A in figure 1. And because for this one, there's no loss of energy because it says ignore the effects of friction, the principle of conservation of linear momentum is applied, and that is how we'd approach this question in particular. We start off with the sum of all initial momentum is equals to the sum of all final momentum, where figure 1 is I for initial and figure 2 is F for final. From here, we have to expand both sides of the equation and solve for our unknown variable, which in our case is the initial velocity of dancer A. So let's get into it. On the left side of the equation, if we expand that one, we end up with the mass of A multiplied the initial velocity of A plus, remember we are summing all initial velocity in figure 1. So we would sum that with the mass of B multiplied by the initial velocity of B. For the right side of the equation, you'd be working with everything in figure 2. So we would then write the mass of A multiplied by the final velocity of A, VFA, plus the mass of B multiplied by the final velocity of B, VFB. From here, we want to isolate our variable of interest. So we want VIA on one side. That means we keep MA times VIA on the left, and we move everything else to the right-hand side. This will then look like MA, the mass of A, times the final velocity of A, plus the mass of B times the final velocity of B minus, remember when you're moving things from one side of the equation to the other side, we have to change the sign. So from what I've written thus far on the right-hand side of the equation, we subtract the mass of B multiplied by the initial velocity of B. From here, guys, we just have to divide both sides of the equation by the mass of A in order to get the initial velocity of A on its own. So let's do so. Note how I'm dividing all terms on both sides of the equation by the mass of A. After doing this, I'm then left with VIA is equals to the mass of A times the final velocity of A plus the mass of B times the final velocity of B minus the mass of B times the initial velocity of B. And all of this is divided by MA. From here, all that's left is for us to substitute in our values into their right places, whereby we're given the mass of A as 52.5 kilograms, the mass of B as 42 kilograms, and the velocity of B as 4 meters per second west. Also, I also need you guys to know that we have to essentially pick our sign convention. So if you're picking west as positive, make sure that everything that's going east is negative. I'll just give you guys a minute or two to find the final answer, and we'll then check if everybody is on the same page. I see that somebody has already posted an answer in the chat, so let's just wait for a couple more people to put their responses in, and we'll take it from there. Okay, from what I'm seeing thus far, it seems as though everybody is on the same page. I am seeing the correct magnitude, but a lot of you guys aren't indicating the direction. Remember, guys, velocity is a vector, so it is a physical quantity with magnitude as well as direction. The correct answer in this case would be 3.2 meters per second, and it'll be west. Some of you have written east. I'm not too sure how you've gotten that. It could be an issue of confusing your convention or your positive and negative directions with the actual terms associated. I'm seeing more east than west, whereas our answer in this case is west. We have to remember our poles. We have north, east, south, and west. What helps me remember is if I go in a clockwise direction, I use the saying, never eat sour worms, in case you guys ever get confused on that. Cool. I am seeing a couple people in the chat asking me to substitute in the values. I'll do so. If I substitute in the values, in place of MA, all right, 52.5. For now, I'm just gonna omit the units. That's then multiplied with VFA, which is that. Cool. So yeah, let me just substitute in all the stuff here, and we will continue on. Since it says that they came to rest, the final velocity of both A and B are 0. Let me just check what's going on, because people are saying I should substitute in the values. In place of the mass of B, I'm going to write 42 kilograms multiplied by 0 because they came to rest. And all of this is going to be subtracted by the mass of B, which is 42. I'm just going to clean this up a bit. Multiplied by, in our case, west is negative. So negative 4. And all of that is divided by 52,5. From here, if you want to find VIA, the initial velocity of A, that then gives us positive 42 times 4 all over 52,5. That then simplifies to 3,2. Okay. Right. I am seeing that the actual answer for this one would be east if we're setting east as positive and west as negative. Sorry for the confusion, guys. Cool. Now that I'm done with that, I'd just like to check in with everybody. How are we feeling about this one? Okay, I'm seeing thumbs up. Hopefully everybody is on the same page and we can move on to the next question, guys. Oh, yes. Thanks for spotting. I do have to include my SI units. That would be meters per second. And I'm going to write my direction, which is east. Cool. Let's carry on. After grabbing each other, dancer A pushed dancer B away with a net force of 670 newtons in 0.5 seconds. And dancer A moves west as shown in figure 3. First of all, let's answer this question over here. What is the net force exerted by B on A? If you guys could please provide the answer in the chat. Right. The net force in this case would be the magnitude is 670 newtons. We just have to determine the direction. Initially, dancer A and B are together, and afterwards, A pushed onto dancer B. A pushed east, so the force exerted by B on A would be 670 newtons west. This one relied on our knowledge of action and reaction forces. Cool. Now let's get to the following question. Let's calculate the magnitude of the velocity of dancer B in figure 3. For this one, we would have to use the impulse formula. We were given the net force as well as the time, so can use the impulse formula. So let's write it down. That is going to be F net times delta T is equals to the change in momentum. We know what F net is, that is 670. Delta T in this case is 0.5. And for the change in momentum, that's going to be mass times, in brackets, velocity final minus velocity initial. This would be the exact same as writing m times vf minus m times vi, by the way. So let's continue on. We want the velocity of dancer B. So the mass in question here would be the mass of B. So let's substitute that in. That's going to be 42, and in brackets, we have VF minus VI. VF in this case is what we want to find, whereas our VI is 0 because we go from figure 2, where they're stationary, to figure 3, where a force is applied and they start moving. So let's get to actually solving this question and getting a final answer. We then end up with VF is equals to 670 times 0.5 all over 42. And that would give us a final answer of 7.98 meters per second. The direction, guys, what direction do you guys think this is going in? Is it going east or is it going west? The direction here, guys, would be east. Remember, east is positive, whereas west is negative. Cool. Now that we're done with this question and we solved this problem, do you guys have any questions for me to answer? Please post them in the Q&A section. Also, guys, if somebody asks a question and I don't happen to see it, you're more than welcome to answer your fellow attendees. Okay, somebody asked, why did we use the mass of B? We use the mass of B because the question is specifying the velocity of dancer B. So we have to use the corresponding mass associated with dancer B, and that is 42 kilograms. I hope that answered your question. Somebody else asked, if I use the mass of A times the mass of A plus the mass of B times the mass of A times the velocity of AI plus the mass of B times the velocity of B initial is equals to the mass of A plus the mass of B VF, is that correct? That wouldn't be correct because they don't have the same final velocity. And Paul's asking, why did I use positive force? We use positive force because A pushes onto B, and that makes B travel. So the force in this question is positive. I hope that answered your question. Cool. If there aren't any other questions, let's move on to the next problem. I just want to check in, is everybody able to hear me clearly? Okay, it seems as though everybody is able to hear me. There was somebody that asked me to, I think, increase my volume or tone. Try see if you can do that on your device, because it seems as though everybody else is able to hear me clearly. Right. Let's continue on. I've given us a multiple choice question that reads as follows. A car of mass A is traveling at a constant velocity and has a momentum of P. The driver notices an object ahead of him and applies the brakes so that the momentum of the car changes to half of P. Which one of the following diagrams below correctly shows the relationship between Pi, the initial momentum, Pf, the final momentum, and delta P, which is the change in momentum? I'll give you guys a quick moment to post your answers in chat, and we'll take it from there. Okay, the answers are rolling in. Some are saying B, some are saying C, some are saying D. Someone else said A. It seems as though majority of us can agree on one answer being correct, and that is B. Answer B. Let's explore why. We have the momentum, which is noted by P, which is the initial, and we have the final momentum, which is half P. The change in momentum is measured by the final momentum minus the initial momentum. So delta P is equals to PF minus PI. That is then equal to half P minus P, which is minus a half P. Cool. What do we know about momentum? Momentum is a vector, so it has magnitude and direction. If we look at the options given, we have to relate what we've just found over here to one of the answers. If we're taking the right as positive and the left as negative, let's see what we end up with. I'm going to start off by just drawing P. So P is just this line over here. This is our PI, which has a value of P. Our PF is going to be half of PI, whereas our change momentum is half of P, but in the other direction. And that's how we end up with B as the answer. I'll just run it through because it seems as though some people were confused along the way. So yeah, we started off over here. We just wrote down that PI is equals to P and PF is equals to half of P. This is stated in this paragraph over here. We then move on to finding the value of the change in momentum. The change in momentum is the final momentum minus the initial momentum over here. All right. From then, I substituted in P and half of P in their relevant places. And I found an answer for my change in momentum to be minus half of P. Cool. From here, I moved on to this over there, whereby I drew P over here, and I then filled in everything else. The final momentum has a magnitude of half of the initial momentum in the same direction, which is right. And that's because I decided to have right as positive and left as negative. From then on, I came back here and I filled in my stuff. I put my P final, which is half of P in the same direction. And I put in my change in momentum, which is also half of P, but in the other direction. And that's how I ended up with option B. I hope this explanation is clear. If not, I'll gladly redo it if the bulk of you aren't on the same page. So can I please get an indication in the chat to just see where we are at? Okay, it seems as though a lot of us over here got lost along the way. That's all right. That's why we're here. We're here to make sure that our understanding of momentum and impulse is at 100%. So I'll just erase everything and start again. Cool. For this one, guys, it relies on us knowing and remembering everything we've been taught about vectors and just a bit of knowledge on what momentum is in actual fact. I'm going to reread the scenario we were given and we'll take it from there. A car of mass m is traveling at a constant velocity and has a momentum of p. I'm going to highlight that in green. So it travels with the momentum of p. The driver then notices an object ahead of him and applies the brakes so that the momentum of the car changes to half of p. Let me highlight that in red. Which one of the diagrams below correctly shows the relationship between the initial momentum, the final momentum, and the change in momentum? Let me just highlight the corresponding things. The final momentum is half of p. The initial momentum is just p. Cool. We want to find what the change in momentum is. The change in momentum is the final momentum minus the initial momentum. Are we all on the same page up until this point? Can I just get a thumbs up, an indication in the chat? Cool. Let's carry on. From the paragraph that we were given, we were told that the final momentum is half of p. So I'm going to substitute that in. Let me actually write it down. Substitute pf is equals to half of p into dot 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 1, where dot 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 1 just means equation 1. That then gives us delta p is equals to half of p minus pi. And the next step is to substitute in the value of the initial momentum. This was also given to us by the paragraph. So I'm writing again, substitute pi is equals to p into dot 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 1, where this dot 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 1 means equation 1. By the way, I just want to save a bit of time by not writing down that whole sentence. This then gives us delta p is equals to half p minus p. So let's simplify what we have thus far. This is then going to give us minus a half p. How are we feeling up until this point? Can I get thumbs up, an indication in the chat? Cool. Let's now get into actually drawing and representing these vectors. We're going to start off by drawing our initial momentum, P, as a straight line heading to the right. In our case, we are choosing right as positive and left as negative. Okay? Cool. This is P. Fine. Now we want to put in our final momentum, PF. PF will start from the same point. Remember, vectors start from the same point in our case, because it's all acting on a single object, which is a car of mass m. And we're going to put PF over here, right? Cool. Next, we have to put in delta P. We could write delta P. We could draw delta P as this, which is half of the length of PI, but we could also draw it as this over here, where we have PI there, we have PF over here, and we have delta P over there. And this matches our answer B. So how are we feeling about this explanation? Can I get an indication in chat, please? Cool. It seems as though we're 100% on this. Yeah. Great, great, great. We could also, if some people here are more comfortable with just working with vectors alone, we could have just started off by having our P going to the right as positive. And then we have our, let me actually do this so that we space. We could just have our initial momentum, PI, going towards the right. And we could have our final momentum as half the length going towards the left, right? This would then give us a resultant vector, because remember, momentum is a vector. The resultant vector in this case, apologies, it should actually, yeah. So you have PI going to the right, and then you have PF going over there. If you want to subtract, you have to flip the direction of one of them. That'll then give us, because it's final minus initial, remember guys, the change in momentum. The change in momentum is the final momentum minus the initial momentum. So we're going to switch the direction of the initial momentum. That will then give us, I'm going to change the color, this right here. Where the black one is our final momentum and the red one is our subtracted initial momentum, right? From here, this then gives us a resultant of half the length of the initial momentum, but pointing towards the left. This is just another way of explaining this, guys, just for interest's sake. But if the first method of explaining was good, then we can just carry on. Otherwise, guys, how are we feeling about what we've done thus far? Can I get an indication in chat, please? Somebody asked, is it still applicable if one uses their own digits? So long as you're able to choose the correct answer and you understand what you're doing, then everything is okay. Right. Please, guys, if you have to leave for any reason, which I'm not recommending, it's better to do it live so that I can answer any questions in case you get confused. We will be posting the recordings of these sessions on our YouTube channel. So please, please, please check out the Learning Space ZA and send these links as well as our social media handles to all your friends so that they can join in on this current session or other sessions we have in the future. Cool. Let's carry on. We have this scenario right here. A 1,100 kilogram truck is pulling an 800-kilogram trailer by means of a massless rope at a constant speed of 45 kilometers per hour. To the right, as shown in the diagram below. The rope snaps and the trailer continues to move to the right with an initial velocity of 9,06 meters per second. Let's ignore all the effects of friction. Again, when we see something about ignoring the effects of friction, we are dealing with an isolated system. So the principle of conservation of linear momentum applies, right? Let's get to solving this question. We'll start off with the first one. Let's calculate the speed of the truck after the rope snapped. Someone's saying I should wait. Wait for what exactly? Could you explain, please? And there's also a request to have the PDF on the WhatsApp community. Yeah, I will share it with the team and they will hopefully share to the WhatsApp community. Cool. Now that we're all set, let's continue on. Oh, okay. You guys are writing a statement, so you can use this for revision. I recommend that you screenshot what we have, and then you could later come back and rewrite or revise if you wish to do so. Cool. Hopefully we're all ready to start. Can we get thumbs up in the chat, an indication in the chat? Okay, great. Paul asked, do we convert the 45 kilometers per hour? Yes, we do convert that to SI units before we start. Right. So let's just start by doing so. 45 kilometers per hour. If we had to convert that to SI units, what would that be, guys? Can you please post that in the chat? Somebody asked if they said we should ignore the air friction, does that mean that the system is isolated? If it says ignore all effects of friction, in this case, it is an isolated system. Unless there is a stated loss of energy, then the system is isolated. Please make every effort to familiarize yourself with the conservative and non-conservative forces, because it'll then help you when it comes to calculations. The knowledge of conservative and non-conservative forces also comes into play when dealing with kinetic energy and all those types of equations. Cool. Right, I'm seeing answers in the chat. Somebody posted 45 times 1,000 divided by 3,600. That is the correct way of computing it. It is 45 times 1,000 all over 3,600. Some of you guys have gotten the incorrect the unit conversion. Please make every effort to revise that. Somebody's asking me to start again. Could you please state from where and at which point I lost you? Or if you could, perhaps post the question in the Q&A section, and from then, hopefully I or one of the other attendees could help you out. Another question is asking, have I done the basics of momentum and impulse, or am I just revising past papers? At this point, we are only doing past paper revision for prelims. And along the way, I'm making every effort to explain the concepts and making sure you guys have a good grasp of what we're dealing with. Okay, somebody's asking, how did I convert? We have 45 kilometers per 1 hour, right? 1 kilometer is the same as 1 times 10 to the power of 3 meters. So that's what we start off by multiplying with. We just change this 45 kilometers to 45 times 10 to the power of 3, which is the same as 45 times 1,000 meters, and that's all over 1 hour. First of all, we have to know how many minutes are in an hour and how many seconds are in a minute. So we then have 60 minutes in 1 hour, and we have 60 seconds in 1 minute. If you do it like this, then the units cancel out. And we end up with 45 times 1,000 all over 60 times 60, which is the same as 45 times 1,000 all over 3,600 meters per second. We haven't forgotten about these units over here. Cool. Right. Let's carry on with the question now that we know what our speed is in SI units. I'm going to just delete what I have right here. Actually, let me rather move it over there. Cool. Let's get to solving this question, guys. I'll just reread the paragraph to make sure that we're all ready to tackle this. A 1,100 kilogram truck is pulling an 800 kilogram trailer by means of a massless rope at a constant speed of 45 kilometers per hour to the right, as shown in the diagram below. The rope snaps and the trailer continues to move to the right with an initial velocity of 9,06 meters per second. Ignore all effects of friction. First of all, let's define our convention. Let's just set right as positive. This then makes this 9,06 meters per second, my apologies, positive. So I'm going to write 9,06 meters per second to the right. And we have that speed, 45 kilometers per hour, as 45 times 1,000 over 1,600 meters per second right as well. I just want to put this into my calculator and see what the actual value of this is so we can continue on with this problem. This is the same as writing down 12.5 meters per second. Cool. Because they said we have to ignore all effects of friction, the principle of the conservation of linear momentum applies. Lebohang, I indicated right as positive over here. I'll just put it aside. Hopefully you guys can see that right is positive. Cool. I'm just going to shrink this to make sure everything fits on the screen. Fine. Let's get to calculating the speed of the truck after the rope snapped. Because we're applying the principle of conservation of linear momentum, we can write that the momentum before the initial momentum is the same as the final momentum. So I'm going to write down here, the sum of all initial momentum is the same as the sum of all final momentum. What differs about this question in particular is that in the initial state, before the rope snaps, all objects with mass are moving at the same velocity. So we can then write the mass of, I'm just going to name this, make sure that B. I'm going to name this B, and I'm going to name this bigger one A. So we can then write the mass of A plus the mass of B multiplied by VI. They both have the same initial velocity, guys. That's what we have on the left side of the equation. On the right side of the equation, we then have the mass of A times the final velocity of A plus the mass of B times the final velocity of B. The objects have a different velocity after the rope snaps, and that's what we are currently calculating. Cool. From here, we have to isolate our variable of interest, which is the speed of the truck after the rope snapped. So we just want to have VFA on its own. If we do so, we then end up with MA plus MB in brackets multiplied by VI minus the mass of B multiplied by the final velocity of B is equals to the mass of A multiplied by the final velocity of A. From here, we divide both sides of the equation by the mass of A and this, I'll just continue it over here, then gives us MA plus MB in brackets multiplied by VI minus MB times VFB all over the mass of A is equals to the final velocity of A. Cool. From here, what's left is for us to substitute in our values and get the final answer. While I'm doing that, can somebody just please post the question or post the answer actually in chat to see if you guys are also on the same page when it comes to us doing the solving and the actual calculations. Ooh, the final answer for this one would be 15 meters per second right. This is a vector, so we are specifying right. Can I get thumbs up or just an indication in chat if I've lost you guys at any point, or if we're all on the same page and you see how we've gotten to this final answer? Okay. Seems as though everybody is on the same page. Somebody just asked, should we include all the steps? For this question in particular, we get a mark for this right here. We'd get another mark for doing all our substitution. Or two, in actual fact, we get 2 for doing this over here. And then we get 1 mark for the final answer, which is that right there. Somebody asked, is the mass of A 1,100? Yes, the mass of A is 1,100. I have indicated with B and A in the diagram. Okay, somebody said in chat that there is no VF. Well, there isn't really a VF in this case because there wouldn't be anything acting on the system that would cause a change in velocity. Remember, we don't have any net or resultant forces acting on this, nor do we have friction acting on this system right here. This is an isolated system. That's why we use the principle of conservation of linear momentum. Cool. Right. If we're all ready to move on to the next question, please can I get a thumbs up or indication in chat? And by the way, if somebody asks a question and one of you guys knows the answer, please answer them because there is a chance that I may not be able to see what they asked. Is this an explosion or collision? We'd be told. We'd be told whether or not it's an explosion or collision. This I wouldn't really define as either. This is just okay. Maybe you could call it an explosion depending on how you look at it. But you're usually told collision or explosion, or you can just determine what's going on. Here we have a single system which is constituted by two parts connected to each other, and that then separates. If you count that as an explosion, then you could say it's an explosion. Cool. Somebody else asked, how do we know that we must use the principle of conservation of linear momentum? We are told by this golden piece of information over here. I'll highlight that in maybe pink or purple. Over here, ignore all effects of friction. When we're told this, we know that we're dealing with an isolated system in which the principle of conservation of linear momentum applies. Somebody else asked, does it matter if it's collision or explosion? You just have to be able to determine what equations to use and and how to arrive at the final answer. Now let's move on to the next question. It then says the truck collides with the wall and is brought to rest in 0.2 seconds. Now we're told that a collision takes place. Because we're given time, we know that it has something to do with impulse, right? So let's get to actually solving this. First of all, I'm going to write down the equation associated with impulse. That is F net times delta t is equals to a change in momentum. Cool. Oh, okay. So I can see that this question doesn't necessarily state what we have to solve for. We have to solve for F net. Cool. Sorry for the mix up there. But for this question, we have to solve for the net force. I've set up the equation right here. So I'll just give you guys a few minutes to try arrive at the final answer. You can ask questions in the chat. Hopefully your fellow students will help you, but I will only come in at the end of the allocated time, which I think I'll give you maybe 3 minutes, 4 minutes, just to see if everybody's on the same page and is following what is currently going on. We have to solve for the net force, F net. And then, meanwhile, guys, if you're done, please head over to our social media pages. It's at the Learning Space ZA. We are on Instagram, TikTok, and YouTube. This is where you'll find the recordings of all sessions we've done. That includes the winter school, the prelim prep, and anything else that's going to come in the future. With a minute to go, I hope you guys are managing to find the answer to this question, or you've at least made some progress. We are the Learning Space ZA. That is our, well, that's our handle on YouTube, Instagram, and TikTok. Cool. Let's get to solving this question. We're going to pick it up from where I left it over here. From this equation that I've written out, I'm going to expand the change in momentum because we are dealing with a track in particular and we are told that it's brought to rest. We're going to use this information. If it's brought to rest, that means our final velocity is 0. Cool. And our time in this case is 0.2. If I substitute, or let me actually expand the equation first before I substitute in the values. I then have m, the mass of the track. So I'm going to write ma is equals, or not equals to, MA is multiplied by, in brackets, I have VF minus VI. We're only using the mass of the truck here because it stated the truck collides with a wall. At this point, the truck is no longer tethered or connected to the trailer. All right, cool. Let's substitute in our values. We have F net times 0.2 is multiplied by, in place of MA, I have 1,100. In the brackets, 0 goes in place of VF, whereas for VI, we use the 15 that we found over here. Remember, in the previous question, it asked us to find the speed of the truck after the rope snapped. That would be VFA for the previous question, that was the final velocity. Whereas for this question, which is a continuation of our scenario, that would then make this 15 meters per second, right? Our initial velocity. Cool. So that's going to be VF minus 50. We're taking right as positive. Cool. We then solve for F net by having that alone on one side and have 1,100 multiplied by minus 15 divided by 0.2, and that gives us an answer of F net is equals to, I'm going to put that into my calculator quickly. That then gives me an answer of minus 82,500 newtons, which is the same as 82,500 newtons left. Cool. How are we with this question? For a question like this, the mark breakdown will be as follows. We get a mark for expanding our impulse equation. Our second mark comes from the left side of the equation. Our third mark comes from this right side of the equation. And our final mark would come from the final answer, which is 82,500 newtons left. If there aren't any questions in chat and everybody is able to see how we arrived at this answer, let's continue on. Somebody asked, why do we use 0 as the initial? 0 is our final because we are told that the truck collides with the wall and is brought to rest. So the 0 would be our final velocity. We're taking that as our final. Cool. Can I just check in, guys? We've hit the halfway point. How are we feeling about the topic of momentum and impulse? If you could just rate that out of 10 for me, just to see where we are now sitting now that we've passed the halfway point of our session. Okay, I'm seeing 10s, I'm seeing 9s, I'm seeing 8.999. Interesting. I'm seeing 7, 6, 8, 8, 5.5. Okay. I'm hoping that this is an improvement from where we were before the session started. We still do have problems for us to grapple with, and hopefully in doing these, we will solidify our understanding of this topic. Cool. We have the scenario over here. A car of mass 1,140 kilograms moving towards the east with a velocity of 30 meters per second collides with an oncoming delivery van of mass 1,650 kilograms. After a collision, the van continues moving forward towards its original direction at 12 meters per second, whilst the car moves at 10 meters per second. The system is isolated. Again, guys, what do we mean by an isolated system? Yes, this is a system with no external forces. There is no loss in energy, and we can apply the principle of conservation of a linear momentum, right? I'm just going to quickly write down the definition of an isolated system. An isolated system is a system on which the net external forces acting is zero. This also means that, yeah, if we have a net external force acting that is zero, we have if net is zero, and based off our knowledge of Newton's laws, if F net is zero, our acceleration is zero. Okay, cool. Let's get into it. For 3 marks over here, we have to determine the magnitude of the initial momentum of the car. Before we do so, we have to start off by defining our convention. Over here, are we going to take east as positive or negative, guys? Which one would you like? Okay, people are saying they want east as positive. That means west. Oh, hold on. I'm putting that correctly. East. East as positive. West as negative. Cool. Let's determine the magnitude of the initial momentum of the car. The formula we use for this one is P is equals to mv, where we just have to substitute in our corresponding values for mass and velocity for the car. That would be 1,140 for the mass, and that's multiplied by 30 meters per second for the velocity. This then gives us a value of 34,200. Write that down. 34,200. My apologies. 34,200. And what are the SI units in this case, guys? The units are going to be kilogram meters per second. Because in this question it's stated determine the magnitude, you don't necessarily have to give the direction, but it is good practice to just state the direction. I'm just going to write east over here. Cool. We want to now find velocity of the van before collision. Remember what we stated about isolated systems. There is no loss of energy, and we can apply the principle of conservation of linear momentum. So let's do so. We have sum of initial momentum is equals to the sum of the final momentum. Before I continue on, somebody asked, the direction I chose at the beginning is that direction you will have at the end. I'm not too sure what you mean by this question. Could you please reword this? Let's continue on. So yeah, if you want the velocity of a van before collision, we're gonna have to apply the principle of conservation of linear momentum. So after I've written what I've written, let's get to expanding what we have. On the left-hand side, we will have the mass of the van times the initial velocity of the van plus the mass of the car times the initial velocity of the car. This is equals to the mass of the van times the final velocity of the van, VFV, plus the mass of the car times the final velocity of the car. Right. We want to find, oops, I made a mistake over here. Let me correct that. Yeah, everything checks out. So let's continue on. We want to find the velocity of the van before collision. We want to find this over here. So let's just isolate it and put on one side. We will have the mass of the van times the initial velocity of the van is equals to the mass of the van times the final velocity of the van plus the mass of the car times the final velocity of the car minus, because we took this to the other side of the equation, we would then have what I'm writing down over here. After this, we have to divide both sides of the equation by the mass of the van. That then gives us VIV, which is the initial velocity of the van, is equals to what I'm writing down over here. Notice how I'm not doing my substitutions until the end. This is just to ensure that I don't mess up with my algebra and I can actually see what's going on if I had to come back to the question to double check my answers. Right. If I substitute in my values, I then have massive, okay. I then have what I'm writing down over here. The van, well, the van is going in which direction now? Because if the car is going east, that means the van is going west. So let me substitute that in now. plus mass of car in this case is 1,140 multiplied by the final velocity of the car, which is given as 10 meters per second. Would that be east or west? That would be east. And if I substitute in everything else, I then get so I'll check and make sure I'm substituting things correctly. Yeah. And this, all of this is divided by the mass of the van, which is 1,650. If I had to solve for this, I then get this as my final answer. I get minus 25,82 meters per second, which is the same as, let me actually write it underneath, 25,82 meters per second west. How are we feeling about what we've done thus far, guys? Can I get a thumbs up or indication in chat? Okay, it seems as though everybody's on the same page. The following question just asked, name and state the principle used to answer question 5.3. Again, that is the principle of conservation of linear momentum. In all that we've done up until this point, we have quite literally been doing the same thing, but they just switch it up in minor ways each time. And I hope you guys are able to see that. Somebody asked, why is the direction west? It is west because we've set our convention. We stated that east is positive and west is negative. We stated this earlier on when we started with this question in particular. Cool. Let's continue on. For the final question, it asks us to calculate the change in momentum of the van. So we want delta P. We set, or we have delta P as equals to the mass of the van, just going to specify V, and in brackets, it's going to be VF minus VI. The mass of the van is constant. It is 1,650 kilograms. The final velocity in this case, guys, what do you guys think it is? It is 12. It is 12. That is correct. It's 12 in terms of the magnitude. We also have to state the direction. So we're going to put down minus 12 over here. And then for the initial velocity, that's going to be negative 25,82. Guys, if you decided to work with a different convention in terms of maybe you said west as positive instead, you should end up with the same resounding answer. Granted that your convention is done correctly and you maintained it throughout the entirety of your calculations. Cool. If you solve for what I've written down over here, I'm going to put that into my calculator and then get I get a value of 22,803. And I am missing something in this case. And a lot of you guys who have gotten the correct answer for this are also missing something, and that is SI units. It's kilograms, meter per second. Cool. We can also state maybe the direction over here and say east. Because remember, east is positive for this specific problem. Cool. How are we feeling about this question, guys? Okay, I'm getting a lot of thumbs up and positive responses. How is the pace so far? Are you guys happy with the pace? Should I slow it down or speed it up? And if you have questions, please post them, guys. Even if you think that they are, even if you think that the question is quote unquote a silly question, oftentimes it isn't. And you find that another student is also wondering the same thing, but hasn't asked yet. Cool. Seems as though some are saying that the pace is fine. Others are saying that I should slow down a little bit. Let's continue on. Right. Over here, we have this scenario. A car of mass 1,125 kilograms, traveling at a constant velocity of 25 meters per second, collided with a tree and rebounds with a velocity of 6 meters per second. The car was in contact with the tree for 3 seconds. Let's calculate the impulse of the tree during the collision. The impulse formula is F net times delta T is equals to the change in momentum. Cool. We haven't, in this case, found what the F net is. We know what the delta T is, but we have everything necessary for the right-hand side of the equation. Remember, guys, this over here, this is the momentum right here. Cool. Let's continue on. On the right-hand side of the equation, let's expand the change of momentum. Because we only have one object that we're interested in this case, that is the car, that's going to be the only mass. So I'm going to write m, where the velocities here, we'll take into consideration the initial and final velocities given. Vf minus Vi, and that's what I put in the brackets. In solving this, we have to substitute in our values. The mass of the car is 1,125. The final velocity would be -6, whereas the initial velocity is 25 meters per second. In this case, we're just taking the direction of the initial velocity as positive. If I had to sketch this out, if I have my, just imagine that's a tree, guys. I have my tree over here, and right here, I'm gonna have my car. My car travels at 25 meters per second. It then collides with the tree for 3 seconds, after which it bounces back. After which it bounces back and has, sorry about that, and has a velocity of 6 meters per second. Cool. Let's carry on with finding our impulse. The final value in this case, if I put that into my calculator, would be I get a value of minus 34,875. And this one is going to be, I have here Newton seconds for the units, which should be the same as 34,875 Newton seconds backwards. For this question, we get a mark for this right here, another mark for substitution, and one mark for units, another mark for direction. Are there any questions on what we've done up until this point? Paul, you stated the correct magnitude and gave the direction as west. You could say that the direction is west, granted that you state in your working out, you're taking the initial direction as east. Cool. Somebody else said, I did not divide by time. I did not have to divide by time because I'm working out impulse. Impulse is the product of the net force and time. Somebody asked, do they not mark the first formula? Unfortunately, not. You'd only get a mark for correctly expanding the formula. Okay. Paul, just to follow up on what you said, if you said in your working out you're taking east as positive as the initial direction, then it would be correct for you to state your final answer as 34,875 kilogram meters. No. 34,875 Newton seconds west. Cool. Let's carry on. We have multiple choice question over here. An airbag can protect a driver from serious injury during a collision. Which one of the following best explains why this is possible? Would it be option A, the time of impact increases, the net force increases? Would it be B, the time of impact decreases, the net force decreases? C, the time of impact increases, the net force decreases? Or D, the time of impact remains the same, whereas the net force decreases? What do you guys think the answer is in this case? The answer for this question in particular would be C. The time of impact decreases, whereas the net force, the time of impact increases, whereas the net force decreases. This over here is impulse. Remember my example I provided in the beginning of the session, whereby if a cricket player wants to catch a ball and doesn't want it bouncing off his hand, or he doesn't want to harm his hand, he will move his hand with the ball, the motion of the ball, increasing the time of impact, therefore decreasing the net force. Cool. Let's carry on. For this question, it reads as follows. A man and a woman, each wearing roller skates, stand facing each other on a flat, frictionless, horizontal surface. The man pushes the woman, and the woman moves to the right at 4 meters per second. The first question asks us to state the principle of conservation of linear momentum. That would be the total linear momentum of an isolated system remains constant. Let me write that down. The total linear momentum of an isolated system remains constant. Cool. The masses, let's continue on to the next question. The masses of the man and the woman are 80 kilogram and 50 kilogram respectively. Fine. How does the impulse on the woman compare to that on the man? Is it greater than, smaller than, or equal to? What do you guys think that is? I just want to get a few more answers before I reveal what the final answer for this is. A lot of people are saying smaller than. I'm going to shock you and say the correct answer for this is equal to. And let me explain why. Impulse, which is what is being asked, we're comparing the impulse of the man and woman, is dependent on the net force and the time. Another way of writing impulse would be maybe the symbol J is equals to F net times delta T, right? For the net force that's happening over here, can we agree that by Newton's third law, every action has a reaction force that is equal in magnitude but opposite in direction, right? So we can then agree that whatever forces are being exerted on each other, whether one pushes on the other or they both push against each other, is going to be the same for both of them. And thus the time that this net force is acting over is still going to be the same for both of them. So the correct answer for this one was equal to. This was a very big shocker. And I think the reason as to why this confused you guys is that this would only apply to momentum and not impulse. Momentum is dependent on the mass of the individual object as well as its associated velocity, whereas impulse is dependent on the net force and the time that the force acts over. All right? How are we feeling about this one? Are we all clear on this answer? Can I get an indication in chat, please? Or thumbs up? Okay, I will repeat it. So the answer for this one is that the impulse on the woman is the same as the impulse on the man because it is dependent on the product of net force and the time that the force acts over. I'm going to explain it over here. Right. Impulse is a product of net force and time, right? In the beginning of the session, I did briefly go over what momentum and impulse are. So, yeah, impulse is a product of net force and time. And we see that it's not dependent on the individual properties of either the man or the woman. This is because of Newton's third law. For every action, there is an equal and opposite reaction of the same magnitude but opposite direction. Think of if you have a box at rest. We have Fg acting downwards as well as F net, not F net, Fn, the normal force, acting perpendicular to the surface. In this case, the object has a net force of 0 because it is not accelerated. Cool. For this question over here, we had to work with the principle of conservation of linear momentum because it was stated over here. That's what was asked first. So that's usually an indication that the questions following will likely rely on that principle. Right. From then we can see that because the force that the man exerts on the woman would be the same as the woman exerting on the man, we can then see that if we go back to this impulse formula, it's going to be the exact same for both of them. They both experience the same net force, and that net force takes place over the same period of time. Was that explanation a bit more clear? Is everybody clear on how we got to the final answer? Somebody asked, if the question asked about the momentum, would it be smaller since its mass and velocity? Uh, yeah, you could say it's smaller, but you'd also have to do calculations to back it up. So, yeah. The recording of this lesson will be posted on our YouTube channel. It's at the Learning Space ZA. This is our YouTube. Cool. Let's continue on with whatever questions we can do in this time that we have left and see what answers we get. We have to calculate the man's velocity immediately after pushing the woman away from him. For this again, guys, we're gonna use the principle of conservation of linear momentum. Let's write down the formula. That is the sum of all initial momentum is equals to the sum of all final momentum. Let's expand the formulas. We'll then have the mass of the man plus the mass of the woman multiplied by 0. That's because they start at rest. Then the force is applied. Cool. And that is equals to the mass of the man times his final velocity, VFM, plus the mass of the woman multiplied by her final velocity, which is VFW. That leaves us with 0 on one side is equals to 80 times VFM plus 50 times -4. That has to, the negative comes from our convention, right? If we solve for VFM, we then end up with 50 times -4 divided by, it's going to be 50 times +4 divided by 80, and that gives us a final value of 2.5 meters per second left. For this question, I chose left as positive. Cool. Are we all clear on how we got to this as the final answer? VI is 0 because they initially start at rest. they are standing facing each other, and then the push happens. So we are just making the assumption that VI is 0, and that assumption will be the correct guess in this case. But we can just see from our logic that the VI is 0. They are standing, yes. Let's move on to the next question. Remember how I mentioned that the impulse on both the man and the woman are the same? This question will just clarify and just show you and back it up with math. So for the first option, I'm going to work with the woman's properties. I'm just going to divide this in half. I'll have F net times delta T is equals to the change in momentum. If I expand this, I then end up with M VF minus VI. This is just option 1, by the way, so I'm going to state it here. Cool. From here, I'm going to substitute in my values. I'm substituting in 50 in place of the mass. In place of the velocities, I'm going to put in 4 as the final velocity and 0 as the initial. Remember, guys, I set my left as positive. So I'm just going to rewrite it over here. If I solve for this, I then end up with 200 Newton seconds left. No. For the woman, it would be the impulse is going to the right, yeah. Cool. Let's do for the man now. Let's do option 2. We're going to start off with the same equation for impulse, which is, write it. I have F net times delta T is equals to the change in momentum. If I substitute in the man's properties and expand the formula, I then end up with 80 multiplied by, in brackets, minus 2,5 minus 0. And this still gives us a final answer of 200, or 2,200 Newton seconds. This one should be left. For this one, yeah. So for this one, I'm still keeping the convention. I have to consider the F net, right? If the man is exerting a force on the woman, she experiences a force to the right, which is negative. That's why I'm putting a negative over there. Whereas because of the reaction force, which is the woman exerting a force on the man, she's exerting a positive force on the man. So that's why I have positive 2,5. And are you guys able to see that we end up with the same magnitude but different directions? And this just confirms the answer that we did, or that we came to over here. With what we've done thus far, guys, how are you feeling about it? We have reached the end of our session. So if you guys have maybe any questions on what we've done, please drop them. Otherwise, please let me know how are we feeling about the topic of momentum and impulse. Let's just rate that out of 10 and see where we're all sitting now. Was there improvement? What things did you learn or find out about today that you didn't know or considered beforehand? And do you guys find the topic of momentum and impulse interesting? This topic is everywhere, guys. It applies to airbags, it applies to sports, kicking, catching, all of that, guys. Even insurance might use it to calculate whatever they have to. If a car hits you and they want to see whether or not you're lying about how far you flew, they'll do the momentum and impulse stuff, guys. It's everywhere. We just have to open our eyes to it. It has been a pleasure, and I hope you guys do join us for all sessions we have in the future. Thank you so much for joining, guys. It's been a pleasure just helping you guys out.